Hello again. Now we're going to talk about the Earth as a system and how the atmosphere fits into that. Before we get going though, let me just remind you of a couple of things that you've got coming up for next week. I'll be back on Friday, January 10th to have an in-class discussion about the cause of the seasons, and then after that we'll be starting to prepare our weather journal. Our weather journal, you want to start, get a notebook to hold this in and put it in. Get it started by next Wednesday at the very latest. Now, if you'd like to keep this electronically, that's fine. It just should be something that's very easy to access. So if you have an iPad and you want to type in your weather journal that way, that's fine. But I don't want it to be something where you have to really fire up a computer and sit down to do it. It should be something that you can jot down your thoughts and observations as quickly as possible. It's not designed to take a lot of time. And the other thing we're going to be doing the following week is building our own weather stations. And I'll talk a little bit more about that on Friday, but you can look in your packet to see what that entails. This is kind of a fun little experiment to build some of your own weather station components to see what goes into that. And it's not going to be a terribly robust weather station, but at least give you an idea of how a weather station is put together. And then I'd also like you to, next Monday, pick up a free copy of the New York Times. They're available all over campus, and bring it with you to class. We're going to be using the New York Times weather sections in class to discuss what's going on in the rest of the country. And they've got a great analysis page in there. The newspaper's free. We can take it apart and do stuff in class about it. Okay, so off to Earth as a system. There are essentially four pieces of the Earth system, and they're listed here. The geosphere represents the geological surface of the Earth, and pretty much everything down to its core. The atmosphere is the air we breathe, the membrane of gases that cling to the Earth because of the Earth's gravity. The hydrosphere is the water on the surface of the Earth, and then we have, at least on our planet, something called the biosphere. And all these things together are what makes up the planet Earth. If we take a look at the distribution of Earth's water, as you know, most of the water is in the Earth's oceans, 97%, a little bit more. The rest of the water is almost entirely in glaciers and groundwater. There's very little water, at least by fraction, in things that we typically think of as water, lakes, streams, inland oceans, and things like that. Almost all of the water is either locked up in the ocean as salt water that we can't drink, or it's locked up underneath the ground in essentially fossilized water that's been buried for a long period of time, or in glaciers. That water does move around the surface of the Earth through the hydrological cycle, and this is because the Earth is a unique place where water exists at what's called the triple point, where it can exist as both water, gas, and solid. And so we have a situation where water is evaporating from the oceans, it's condensing into clouds in the atmosphere, those clouds move around, they precipitate out onto the ground. That water that's coming down from precipitation interacts with the soil and creates weathering, which drives the erosion of the land. That eroded sediment gets transported back to the oceans and deposited at the subsea floor. Now that's what's happening in the atmosphere. What's happening in the geosphere is that subduction from plate tectonics is pulling down that deposited sediment down deep into the Earth, where it gets melted and rises up again through volcanic plumes, and that gas comes right back. The water that's locked in there comes right back into the atmosphere in that regard. So this is the place where water can go. The water spends different amounts of times in different areas, depending on the current physical system. The water spends a different amount of time in each area, but it does go through this entire cycle. Now, if we think about the composition of the atmosphere is primarily nitrogen. Nitrogen is a non-reactive gas. N2, it's in the form of molecular nitrogen. A good fraction of the rest is oxygen, about 21%. That's the stuff we breathe to live, so it's good that it's there. The only reason there is oxygen in our atmosphere is because there's life on planet Earth. Plants take up CO2 and release oxygen, and we haven't always had an oxygenated atmosphere, but the fact that we do means that we can support animal life on this planet. The rest of the atmosphere is either a noble gas of argon or krypton, things like that, or things like water, methane, those sorts of things. Carbon dioxide makes up about, that says 387 parts per million. It's about 400 parts per million now and growing due to the human influence on the CO2 cycle. Now, we usually put these things in percentages, but when the percentages get small, it's easier to talk about parts per million. A percent is a part per hundred, and you could say pph instead of percent. We usually just say percent, but in parts per million, is listed as ppm, and it means that you've got one part for every million of everything else. Now the carbon cycle is, again, unique to this planet as well, because we have plate tectonics which moves the carbon around. And so there are sources of carbon and there are sinks for carbon that interact with the atmosphere. When we burn any sort of biological matter, we get carbon dioxide released to the atmosphere. So this is if we're burning trees or forests or fossil fuels for that matter. There's fossil fuels right over here. Burning of fossil fuels releases CO2. The only difference between these two sources of carbon dioxide is the fossil fuels have been buried for a very long time, so they're not part of the annual cycle or even multi-year cycle. The trees and plants, however, are part of the annual cycle. So burning of biomass does not contribute to the overall amount of carbon in the atmosphere because that carbon was taken up by those trees to begin with. Burning of fossil fuels, on the other hand, does contribute to the overall amount of CO2 in the atmosphere because we've dug the fossil fuels out of the ground and burned them into the atmosphere. Other sources of carbon dioxide is weathering of rock, volcanic activity, respiration, so this is us, we breathe out CO2, and you get photosynthesis, which is both a source and a sink of carbon dioxide depending on the species of organism that's doing it. Okay, so what about sinks for carbon? We've got the burial of biomass, so this is if we have things die and get buried in sediment, then that removes carbon from the atmosphere or from the ground. Photosynthesis by vegetation, like I mentioned, plants take up CO2 and release oxygen when they do that. If we weather granite rock, that can take up CO2. If we deposit any of that weathered stuff into the ocean, or we even dissolve CO2 into the ocean in the form of carbonic acid. So this is how carbon cycles through the atmosphere. The thing that's of critical importance right now, at least as far as the climate is concerned, is this right here. This is the new thing that we're adding in, burning of fossil fuels. There's a little bit of this as well because we're tearing down and burning forests to create farmland. And if we burn the CO2 from the forest, that doesn't necessarily impact the amount of CO2 in the atmosphere, but if you never replant that forest, that does impact the amount of CO2 in the atmosphere because the plants aren't there to take it up. So those are the two things that human beings are now completely in control of, and we're on track to double the amount of CO2 within a... So a lot of the carbon that gets taken out of the atmosphere gets locked up in the Earth's geosphere. And how does that occur? Well, when the carbon gets washed into the ocean, it gets taken up by organisms which use it as part of their shells. And then those organisms die and they fall to the bottom of the ocean and they get locked up in the sediments at the bottom of the ocean. Ultimately, those are subducted into the Earth's mantle. You can see some of these shell fragments up close. Right here, this is all carbonated carbon material. The other place that CO2 can go is being uptaken by photosynthesis, but it's also the primary source of the Earth's oxygen. Now this is something that's interesting to me as an astrobiologist because the fact that we have a signature of oxygen in our atmosphere means that life is on this planet. If life was not on this planet, we wouldn't have any oxygen. The oxygen would react with everything else and it would go away in a very short period of time. So the atmosphere really is an indicator of the life on the planet, and it really is the breath of the planet. The life on this planet breathes the atmosphere in and out. Here's an example of the measured increase in carbon dioxide that's due to human influences. So this started with an observation back in 1960, and again we see this breathing in and out of the atmosphere that's due to the respiration of the organisms on the Earth, primarily plant life. The plants would take up more CO2 in the summertime, and then when they would decay or drop their leaves in the wintertime, they would release CO2 and back and forth. But there was also this very noticeable trend, especially over several decades, of an increase in CO2. And this is an exponential increase in CO2, and like I said, it has a doubling time of about 100 years. The other thing that human beings are beginning to impact a number of other areas of the atmosphere in two particular areas. One is air pollution, which you can see here in the satellite photograph. This is a satellite photograph near Korea. This is North Korea and South Korea right here. This is China. You can see the air pollution coming from China. And also dust storms, while a natural phenomenon, as we tear up more land to put in farms, that creates more land that can be a source for dust storms. So we can see the impact of dust storms, which can be due to deforestation, and also air pollution, which is due to the pollution in our cities. Now, we're all familiar with this here in Ogden, Utah. We get aerosols in the atmosphere. They can cause colorful sunsets, but they also cause a heck of a lot of trauma for people with lung ailments. But again, we can see the impact of the human beings on the composition of the atmosphere. Now, there's another area where human beings have had a strong impact on the atmosphere, and that is in the reduction of the amount of ozone in the upper atmosphere. Now, ozone is a protective chemical which blocks UV radiation from the sun and keeps it from getting to the surface of the earth, which is good because UV radiation can cause cancer and creates some health issues. It was noticed a couple decades ago that there was a reduction in the amount of ozone that we saw in the atmosphere, in particular over the South Pole. And so what this is showing the size of the ozone hole as a function of time during the year, function of time during the year for 2 different years. And we see that in 2006, at the peak of the southern summer, we were getting the largest ozone hole, larger than even the size of North America, and it didn't decrease until December. This is it in 2007, and we noticed that there's been some improvement. And the reason that there's been improvement is because the cause of the ozone hole was the release of what are known as chlorofluorocarbons through mainly refrigerants and hairspray and other propellants in spray cans that would get up into the upper atmosphere and cause havoc with the chemistry. They would react with the ozone and scrub it out of the atmosphere. And as soon as this was noticed, there were a lot of international treaties that went into effect to reduce the amount of chemicals like these that were used in industry. So this is a picture of the ozone hole in 2007, and again, we put these treaties in place, and we look at the effect of those treaties. We were rising up in 1980. The hole was getting bigger and bigger and bigger. Right around 1995, we started to implement some of these changes, and then we see that the ozone hole has effectively stayed about the same size, and it even looks like it might even be getting a little smaller. So that's a huge success story that we managed to see our impact on the climate, or impact on a property of the atmosphere, and reduce that impact by passing international treaties. Here's a prediction of what we think the range of ozone will be going into the future, and we can see that this was our modeled observations of the ozone change from 1980. It was getting smaller and smaller and smaller and smaller and smaller, the amount of ozone, and then we enacted some of these protocols, and now they're going back up. So we expect there to be about the same amount of ozone as there was back in 1980 by about 2030 or so. So again, this is a great success story of human beings seeing their impact on the climate and doing something about it. Okay, let's talk about the structure of the atmosphere itself. The atmosphere is a three-dimensional object that surrounds the entire Earth, and when we go up from the surface, we go up to different elevations, the pressure of the atmosphere drops. Now that pressure is measured in a unit called millibars, and 1,000 millibars, or 1 bar, is about sea level atmosphere. So it's what the atmosphere that you would experience at sea level. And as you go up in altitude, you see that the pressure drops off. So where are we here in Utah? We're a little bit less than a mile high, and we have an atmosphere that's slightly larger than 800 millibars. If you go up to the top of Everest, you get down to 300 millibars. If you go up to where the high altitude balloons go, you're down to 9.6 millibars, which incidentally is about the same atmospheric pressure as the surface of Mars. So you have to go up to 100,000 feet to get to about the surface of Mars. Pressure that you'd see at the surface of Mars. In addition to pressure dropping, temperature also drops, and you can see that by living in Utah by just looking up in the wintertime. You'll see an area that has no precipitation of any kind, and then you get up high enough and you'll see ice and snow. So that tells us that the temperature does drop with altitude. The structure of the atmosphere is something we measured with atmospheric balloon experiments, and we see that as you go up, it does get colder initially until you hit what's known as the tropopause. And then as soon as you hit the tropopause, the temperature actually increases. And the reason for that is because that ozone we talked about is in the middle of the stratosphere. And that ozone is absorbing solar radiation and heating up when it does that. And so the atmosphere is cooling as you go up to the stratosphere, but as soon as you hit the stratosphere, it heats up because of that ozone absorbing the solar radiation. Once you get above the stratosphere, there's no more ozone to absorb any radiation, so we begin to cool again. That's called the mesosphere. And then once we get past the mesopause, we get into what's known as the thermosphere, and this starts to warm up again due to interaction with particles from the solar wind. The interesting thing about this is that the fact that we have what's known as the tropopause in the stratosphere, the fact that we have this temperature inversion means that our weather conditions are pretty much restricted to everything below about the height of 10 kilometers, about 8 miles. And the reason for that is because any of the water that is in the lower atmosphere, if it rises, it gets to the point where it gets cold enough that it freezes out or it condenses out into clouds before it gets up to this point. And so this acts as a kind of a cold trap to keep all of the water molecules in the troposphere. So what about the height of the tropopause? The height of the tropopause is determined by latitude on the planet for two reasons. One, because it's colder near the poles than it is at the equator, so that that's going to tend to lower your tropopause. But also, we have a spinning Earth, which means that the atmosphere has a little oblateness to it. And so near the equator, near the band that we're spinning around, we tend to have a thicker atmosphere. And so this is a graph just showing that as you go up, the place where you turn over into the stratosphere will happen sooner at the poles than it does at the mid-latitudes or in the tropics. Okay, so that's a little overview of the Earth as a system. When we meet on Friday, we're going to talk a little bit more about how the Earth interacts with the Sun to get energy from the Sun, as well as determine when the seasons occur. And I look forward to seeing you all on Friday.